Hi guys, in our first video I had promised to do a next video on hybridization of atomic orbitals, and this is going to assist us, of course, see how carbon in its diverse characteristic is going to form covalent bonds with other elements. So in a sense, for our illustration for today, it's going to show us the concept of hybridization of atomic orbitals, and basically we're going to look at carbon as an example in this particular case. And from the concept of reactions that we had spoken about, we see that chemical reactions basically occur due to interaction of valence electrons from a particular atom with that one of another element. And therefore, elements form covalent bonds by overlap over these particular atomic orbitals. And for the ones which are involved in the covalent bonding, therefore, we're going to see that there's a pair of electron which is going to be shared by these different species of atoms. This implies that only orbitals with a single electron are going to be involved in chemical bonds. Of course, we're going to look at different types of bonds. I've mentioned the term covalent bond, and I've said that information of these orbitals we're heavily going to rely on this one, especially now that we have said carbon basically form covalent bonds with other compounds. So therefore, as we expect a single bond, or rather single orbitals with single electrons to be involved in chemical bonds, for covalent bonds, we're going to see there's going to be an overlap and sharing of these particular electrons from the valence shells. However, for the case of carbon, we're going to see that it's capable of forming 4 identical covalent bonds, even though it has got 2 lone pairs of 2 unpaired electrons, as we had demonstrated from its electron configuration, which we can basically give us 1s2, 2s2, and then 2p. This was 2p4 this was 2p2 from our illustration as we had done earlier. So in this case, we're going to see that this one consists of a single orbital, while this one consists of 3 orbitals. And this is the, of course, it's going to be illustrated now from the assignment of electron configuration. We had expanded this one and shown that for the 1s orbital, this one consists of 2 electrons, which are going to be shown as this. And for the 2s orbital, also this is going to contain 2 electrons in its orbital as that. Now for the 2p, we're going to have for the x, y, and z, whereby the first 2 sets for x and y have got a single, of course, electron each given as such. So there's a z orbital which is not containing an electron in that particular case. And now due to orbital hybridization, of course, of the atomic orbitals within this particular atom, we're going to see that the new set of identical orbitals with intermediate energies are going to be formed. And this is going to be illustrated from the diagram that I've given on the upper part of the table, which I'm going to elaborate on later. Now for this particular single orbitals in the s subshell, of course, which is the second one, it's going to overlap with 3 orbitals from the p subshell to form newly 4 hybrid orbitals, which are going to be referred to as sp³ hybrid orbitals, which I'm going to show later as I've mentioned. Now this particular case for the sp³ hybrid orbitals, these are going to display, of course, a greater p characteristic. Now that we have mentioned on different shapes of orbitals, therefore they are going to display p characteristic. Therefore, we are going to expect them to appear as having that particular damper shape, which is more pronounced as compared to the spherical shape for the s orbitals, as we had mentioned earlier. So therefore, in terms of quantifying it, we can say that it's around 3/4 of that particular shape is going to be consisting of the p orbitals, therefore going to give it that particular shape. So if you try to look at the diagram that I've given on the board, therefore, we can be able to illustrate this particular case whereby we're going to have an interaction between these orbitals from the 2p mixing or overlapping to form the sp3 hybridized. This is just a combination. This is an illustration for the combination of the two orbitals which are going to form that one. And of course, in trying to look at these two s orbitals is going to be excited, and this one electron is going to move into this empty shell. Therefore, there's going to be hybridization of these two sets of orbitals, which are the two s orbitals and the 2p orbitals, which are forming the valence orbitals in that particular case. Now, the newly formed orbital, which is an sp3 hybridized, is responsible for a single bond formation in carbon. So this is for the single bond formation in carbon, and therefore we expect it to form this range of organic compounds, like or to be displayed in this class of organic compounds that we refer to as the alkenes. And therefore there are other subsequent hybridization, of course, that we're going to have, which are going to have different effects. For instance, if we're trying to look at this, there's a second category of hybridization whereby we are going to have an sp2 hybridized molecules, whereby the hybridization involve a single orbital in the s subshell and two other orbitals from the p, which are going to form three new orbitals referred to as sp2 hybridized. And in that case, of course, we're going to see that the orbital, one of the orbitals in the sp, in the p orbital, is going to remain unhybridized. And that one we can be able to illustrate it using this specific diagram, whereby we are going to have this particular set of orbitals for the p orbitals. You can just do it using do away with this. So we're going to have this one illustrated as the p orbitals lined along that specific line, and another one. So this is for the z, x, this is a y, x. So therefore, if we are having this one as the, you can as well have this one. We had a three-dimensional space, but of course I'm just going to align them along this axis. Therefore, we are going to have a single set of this is the pz orbital that is going to remain unhybridized in the case. So we are going to expect therefore either the px and the py axis to be hybridized, and therefore one of the orbitals of the p subshell is going to remain unhybridized in this particular sense. So in this case, if the y and x orbitals are hybridized for this particular case for the p, and therefore the z, either the z or the y or the x is going to remain, either one of them remain unhybridized. Therefore, we're going to have the sp2 hybridized, which means the an orbital from the s and two orbitals from the p are going to be mixing up to form the sp2 hybridized orbital. This results, as we had said, that the sp3 hybridized orbitals result in the formation of a single bonds. The sp2 hybridization results in the formation of double bonds. And next, we're going to also to see that there's another category of hybridization that is going to result in the formation of a triple bond, whereby you can just do that one using an illustration, which is going to be more clear. So we have stated that one of the bonds is formed due to the head overlap of respective sp2 hybridized orbitals, whereas the second bond is formed by sideway overlap of the corresponding unhybridized p orbital. And such a bonds are referred to as a sigma bond. And we're going to see that if we try to illustrate that one, just going to have a shape on the board. Now for the sp2 orbitals, we have said that one of the bonds will remain unhybridized, and we have given an example. Let's say this is the y-axis, and therefore there's an overlap that is going to be realized due to this unhybridized orbitals, which is going to form what we refer to as a pi bond, whereas the head-on overlap of this specific orbital, whereby we are having these electrons, therefore it's going to result in the formation of another bond that is referred to as a sigma bond. Therefore the sigma and the pi bonds in this particular case are going to form a double bond, especially for the compounds of the class of organic compounds that we refer to as alkenes. And therefore this is how we can be able to illustrate on how that specific sp² hybridization of course occur. So therefore we're going to remain with this one view, y and hybridized orbitals we have said, whereas in the case of sp³, there are of course the orbitals, the valence orbitals for the b subshell are all hybridized, therefore resulting in the formation of a single bond. So for the third case, we're going to have a sp hybridization, and in this case for the sp hybridization, only one of the three orbitals mixes with a single s orbital to give rise to two new hybrids referred to as sp hybridized orbitals. And this means that the p orbitals remain unhybridized in this particular case, and therefore we're going to see that the difference between the sp² and sp hybridized is that two orbitals are going to be, of course, all the p orbitals are going, the two p orbitals are going to remain unhybridized, and in this sense we can just give a different illustration for this, whereby we're going to have a side overlap for this unhybridized orbital for the pi bond. So we're going to have two pi bonds apart from the sigma bond that is sp hybridized at this particular case. So if I choose this particular point and this one, so we're going to have this one as another pi 2 bond. This is the pi 1 bond. Therefore we're going to have 1, 2, 3 bonds in this particular case, and this is going to give us the sp hybridization of this orbital. And this kind of hybridization is responsible for the formation of triple bonds, especially in a class of compounds that we refer to as alkynes. So alkynes and analogous compounds that we are going to see are going to comprise of that sideway overlap of the corresponding p unhybridized orbitals, and therefore are going to form those particular corresponding bonds. So basically for hybridization of atomic orbitals, we're going to see that there's an interaction, insofar as carbon is concerned, there's an interaction of the 2s and p 2p orbitals, which basically appear the valence shells, and therefore these are going to dictate on the nature of hybridization that is going to occur insofar as these atomic orbitals are concerned. Now, in this case of focus of hybridization of atomic orbitals is going to shed a light on how these organic compounds are going to be formed. And as we said that they are going to give us a clue on how we can be able to detect, or rather try to explain different molecular shapes that we're going to encounter in our next or following videos that we're going to do on shapes and perhaps figures that are going to represent molecules, and particularly organic molecules which are going to be formed from this particular overlap of atomic orbitals. Now for this we will also have to stop there. Now I'm going to put a link of these other related videos in this description box of this particular video, so that we can be able to check on them and see how the relationship of this discussion with others is going to assist us, especially on the concept of organic reactions and the synthesis. So that is it for now, guys. Bye. God bless you.